Hello team, we're going to go ahead and do a quick little video here. In this video, I'm going to be using some terms like heat and specific heat capacity. We're going to use this equation that relates heat, which is the flow of energy, to a temperature change. And so before I get into a sample problem, let's go ahead and just talk a little bit about this equation. I'll start over here on the left. Here's Q. Sometimes I'll write that as a big Q, capital Q, or a little q. We're going to be in units of joules on this particular video. And this is the flow of energy from one place to another. And it's very important that we keep track of the idea that the sign of Q has really important meaning here. And so if I have an object and it's going to lose energy from beginning to end, then Q is going to be a negative number. How do we get that negative number? It tends to happen over here off of this change in temperature, final minus initial. If you start at a high temperature and you go to a lower temperature, then this is going to have a minus sign, which is going to be met by the minus sign that would be held over here on a Q. Okay, and then the opposite must be true. If I'm gaining energy, Q's are going to have plus signs. So my mass is defined here, and this is going to be in units of grams. The reason why that's important is because my specific heat capacity in this particular problem is going to have units of joules per gram per degree Celsius. So this is a property of a material, and what it tells me is either how much energy, so looking in the numerator here, how much energy it takes to raise 1 gram of that material by 1 degree Celsius. Or if we're working in this losing energy, it's the amount of energy given off, so in joules, as 1 gram of that material drops by 1 degree Celsius. Okay, so here's the problem that I'd like us to do in this particular video. So I'm going to have a stone that is given as 19.5 kilograms, and I'm giving the specific heat capacity of 0.88 joule per gram per degree Celsius. And I'm telling us that it's initially at 42 degrees Celsius. That's pretty warm, maybe in the hot sun or something like that. If this stone loses 1.8 E5, so this is 180,000 joules of energy, what will be its final temperature? So I'm going to come in here, and first I'm going to note that this is a loss of energy, and it's going to be on me to make sure that I get my minus sign in here. And so I'm going to go ahead and plug in from left to right the values that I have here. So a loss of this much energy, I'm going to put in a minus sign. 1.8 E5 joules is equal to the mass. If you look carefully here, I was given the mass in kilograms, and I'm going to want that mass to be in grams. So let's just grab this separate little piece here, or maybe I'll do it down here off to the side. I'm going to have 19.5 kilograms. I'm going to do my unit conversion, kilograms going to grams. Every 1 kilogram is 1,000 grams. And so this is going to be 19, this time, comma, 500 grams. 19,500 grams. Now I'm ready for my given specific heat capacity, 0.88 joule per gram per degree Celsius. And delta is always final minus initial. And so I would have my T final sitting here, which is the thing I'm actually trying to find, minus 42 degrees Celsius. I'm going to do a little trick that I like to do, and I encourage you to do. I'm just going to first solve for delta T as is, and I'm not going to go ahead and split this out into its other two terms yet. I'll do that right at the very end, but this is going to save me a little bit of distributing mathematical terms over here. So what I'm going to do is I am going to start with this number, and I'm going to divide both of these numbers over into the denominator under this, and I'm going to solve for delta T here. So negative 1.8 times 10 to the 5 divided by 19500. Okay. And you can see here that I have already solved for delta T, and it is minus 10.4 9. I'll round it there. Before we get too much further, let's go ahead and do a quick sig fig check on this. Right here I have 2 sig figs, I have 3, I have 2. This really is only going to be good to 2. I'm going to not round it quite yet though. Let's go ahead and leave it like this. Now I'm ready to come down here and write delta t is equal to t final minus t initial. T final is truly the thing I'm solving for. If you forgive me, I am realizing that I forgot my minus sign in there. So let me go ahead. You can see it was on the calculator. So I have minus 10.49 degrees Celsius is my delta t is equal to t final minus t initial was 42 degrees Celsius. So let's add this over to the other side. So plus 42. And I find that t final is equal to 31.51 degrees Celsius. Remember, the addition and subtraction process when it comes to significant figures means that I care about the location of the decimal for what I'm allowed to hold. So I'm good with the ones place. I do not know the tenths place, the 0.1 digit. So I cannot be knowledgeable of that here. So I'm going to need to round this to the nearest one. So I'm going to say T final is now equal to 32 degrees Celsius, and that's going to be my final answer. Okay? Move that up just a little bit to make sure you could see that. All right, there's my completed problem. So hopefully that was a helpful video for you.